So I hope everyone can see my presentation. Okay. So hello everyone. Thank you for coming to my talk, and I'm happy to be here. And thank you for Eliza to invite me for this presentation. So today I'll be talking about the interplay between adaptivity, efficiency, and constitutive modeling for fluid simulation. And this is basically an overview of the research that I have been conducting at Rutgers over the past few years. So I have organized this talk as shown on this slide. And before I dive into the details, I thought that it might just be a good idea to spend just a few minutes to talk about why I think digital modeling and simulation is a nice area of research. So, um, as you know, this field has had immense success in the visual effects industry, um, as is quite obvious with uh, amount of CG we see in feature films, and the technology has matured just so much that we cannot even tell the difference between reality and CG. But the nice thing that has happened is as this technology has started maturing, it has also started branching out of visual effects, and it has started finding use cases in other research areas also. So, for example, computational biomechanics and virtual surgery and CG methods can provide here the ability to visualize phenomena that is otherwise not possible with conventional techniques. And the industry is also aware of this development, and new startups are constantly emerging in this area. So, as another example, autonomous driving cars are a very active area of research these days, and a good physics simulator is important for predicting the effects of environment, such as you see in this slide where this autonomous car is driving on a muddy terrain. So again, this is a very active area of research, and new startups are constantly emerging in this discipline. Now, some of the underlying mathematical tools in simulation, uh, which is the theory of numerical methods, also find use cases in some other non-intuitive fields, such as the design of math libraries that always give the correctly rounded answer by construction. And obviously, the appeal of computer graphics has value in graph visualization. So that's also an interesting area of activity. Then simulation tools are also value for motion planning in robotics, particularly for robotic platforms such as the tensegrity platform shown here that has a very high number of degrees of freedom. And finally, simulation also has importance for predicting disease spread in dynamic crowds. So this was our attempt to model COVID spread in open crowds, and this is a very recent work coming out of my lab. So please feel free to check my website for more details. Okay, so with that said, my research basically looks at the underlying computational models, the associated data structures, and numerical solvers, and how they interact with the underlying hardware to allow high quality simulations to run on commodity workstations. So, to give an idea of the kinds of simulations these techniques have allowed to do, here is an example where we are showing airflow in the human respiratory tract. And just to give you an idea that there are approximately 2 billion variables that are inside this human bronchi to capture the level of detail for the fluid simulation that is being shown. And um, basically, this simulation is also running heterogeneously on a computer with 6 GPUs. So, In terms of comparison, if you were to use conventional methods to run this kind of simulation, then you would need over 13 terabytes of RAM and probably several months of computation. And this entire simulation fits on a single computer and finishes in a couple of days. So one of the goals that I plan for my research is to ultimately enable a platform that allows computational dynamics as a network service. And the idea here is that there is a lightweight client, such as a tablet or a laptop, that can be carried on the field that only sees the essential output, and the heavy computation is offloaded to a remote server with specialized hardware that can do all the heavy computation. So, in that light, I'll be describing some of the progress we have made in the area of fluid simulation. And broadly speaking, fluid simulation has two primary stages. It has an advection phase that advances quantities forward in time, and it has a projection phase that enforces incompressibility. Now, the exact jargon here is not so important. What's important is to understand that the advection phase involves a streaming operation that basically involves some local mathematical computations, such as interpolation, and the projection phase requires the solution of a large and sparse linear system. Now, fluid simulations can be massive. For example, if you're trying to simulate the weather, or if you're trying to predict the effects of a tsunami wave. So we require efficient data structure that can handle these massive amounts of data. Also, compute platform these days is becoming increasingly heterogeneous. So two examples are shown here, which is a computer fitted with multiple GPUs, or the Intel Knights Landing framework that has a 16 GB fast RAM and a slightly slower RAM with over 192 gigabytes of RAM. So let me first talk about how can we design efficient data structures to accommodate extremely large amount of degrees of freedom. So we require three things out of these data structures. We require them to be memory efficient and scalable to massive problem sizes, and we also want them to be cache optimized for maximum performance. Now, unfortunately, most of the computational domains that arise in the real world tend to be highly irregular, and these pose obvious challenges in terms of exploiting cache locality and parallelism. So, interestingly, the industry is already aware of this problem, and they have their own solution for solving this problem, which is called OpenVDB. And as you can see on this slide, it was used for rendering massive cloud datasets in the movie Puss in Boots, or for rendering particle-based fluids in the movie Battleship. Now, the particular solution that I am going to describe, which is called SPGrid, tends to be 3 to 5 times faster than OpenVDB for two of the operations that arise most commonly in fluid simulations. So, what exactly is SPGrid? SPGrid is short for sparse page grid, and it's a data structure that exploits the virtual memory management system in conjunction with a Morton-Ordwin scheme to efficiently store and process large amounts of data. So I designed SPGrid with several goals in mind. I wanted the ability for fast sequential and local operations to speed up the advection phase of the fluid simulation pipeline. I wanted the ability to store multiple data channels that correspond to different physical variables, such as pressure, velocity, temperature, and so on. And I also wanted to maximize the use of the available memory bandwidth for maximum performance. So to understand how SPGrid works, let's just look at a simple example. So suppose we have a giant domain where we are only interested in a small narrow subset. Now the naive approach here would be to just go ahead and allocate a dense array on the entire computational domain. But as we know from experience, if our domain is too big, then we'll end up wasting a lot of this allocated memory. So I follow a different paradigm where I use this mmap function call from the Unix environment, but this is just a placeholder because only those entities that are actually touched are stored in physical memory. Now, ideally, we only want to store those entities that are closest to my narrowband of interest. And this brings up the question of how do you index into this dataset? If you were to follow lexicographic indexing, then each 4 kilobyte page will use very low utilization. So here we are just giving a ballpark of approximately 10%. So what you want is something that is more compact, as shown here, and this can be achieved using a Morton ordering. And this is a concept that is also used in computer architecture for designing page tables. So SPGrid in fact uses a hybrid ordering where it organizes data into blocks. Now entities within a block follow lexicographic ordering and blocks themselves follow a Morton ordering. So to understand how this indexing works, let's just look at four of these 4x4 blocks. And just for our understanding, I have enumerated the entities inside these blocks according to their linear index. So if you look at the binary expansions along the coordinate axes and any one particular index, then you can see that that index can be computed as a simple bit interleaving operation. And the catch here is that this operation can be done extremely fast in modern hardware. Now, similar operations can also be done for locating the neighbors of a particular element, and this is required for constructing the large and sparse linear systems during the projection phase of the fluid simulation pipeline. So here is one example, another high-res simulation that is facilitated by this data structure. And here, as you can see, there is inflow from below that is twisted because of these multiple twisted tubes. So that creates a lot of vertical details. And here we are actually coloring the flow according to the vorticity of the underlying fluid. So blue represents high vorticity and red represents low vorticity. So just a quick conclusion that I've described to you a data structure that uses virtual memory and Morton ordering for storing large and sparse data sets on uniform grids. Now, I haven't told you all the details here because technically we also need a solver to solve for these large number of variables. So essentially the linear system that we construct. And in this case, we are using a hybrid solver that is running part way on the CPU and part way on the GPU. But I'm not going to describe this solver in this talk because it's very specialized for uniform grids. And what we want is the ability to adapt the resolution where we think more details are going to emerge. So that brings me to the next topic in this talk, which is the design of adaptive solvers for scalability. So adaptivity is a common problem that has been studied in computational geometry, and there are adaptive data structures such as this conceptual quadtree shown on this slide. So these quadtrees are conventionally represented using these tree-based data structures shown on the right. And so as a consequence, they have pointer-based implementation. Now, collateral consequence of this design choice is that neighbor lookups require moving up and down the tree that requires expensive pointer dereferencing operations. And these operations are very slow. So the typical rule of thumb is that for the same number of degrees of freedom, an adaptive data structure is roughly 10 times slower than a uniform data structure, such as a uniform grid. So one of the design changes that I made was that instead of using this tree and pointer based representation, I switched to using a stack of sparsely populated uniform grids. Now, A thing to notice is that simply using the stack is not enough because neighbor lookups will still correspond to moving up and down the stack. That requires this indirect referencing, which will be expensive. So another observation was that typically in fluid simulation, we never require the exact answer for any algorithmic kernel at one point in space, but at all points in space. So operations can be performed in bulk, and this can be done very efficiently through the concept of ghost cells. So ghost cells are essentially an alias for a cell that lives at a coarser level, and the idea is to first upsample the value of the core cell into its ghost children and subsequently only perform local operations at a single level. And this maximizes the use of the available hardware memory bandwidth. So the general idea is to first upsample the values of the course parents into the ghost children, and subsequently only perform operations at a single level, and this maximizes the use of the available hardware memory bandwidth. And once this stage is done, then there's a downsampling phase where we accumulate the values of the ghost children into their course parents. And what we showed is that these three operations are enough to emulate every algorithmic kernel that arises in an adaptive fluid simulation pipeline. So having done this, we also require a solver for efficiently solving the sparse linear systems that arise. And for this purpose, I designed a multi-grid solver. So just a quick review of what is multi-grid. As the name suggests, it's a multi-scale method, and it has four building blocks. It has a smoothing routine that removes high frequency noise. It has upsampling and downsampling operator for coarsening and refining the problem, and it has an exact solver which solves the problem exactly at the bottom. So the idea of multi-grid is to selectively coarsen the problem until it's efficient enough to be solved exactly, and then upsample the solution to the finest level. So the easiest way to understand the benefit would be to consider a test problem. So here there's an adaptive domain with three levels of resolution, and the exact solution looks like a tent function. Now, just for the sake of comparison, I'm showing the convergence of another solver, which is called incomplete Cholesky preconditioned conjugate gradient, and this is the industrial standard for solving these kinds of problems. Now, as you can see, this solver takes a lot of iterations to converge because the waves of correction have to continuously propagate back and forth. So it's quite slow. Now, in contrast, if you observe the convergence of multigrid, then it completely solves the problem in roughly 10 iterations. And basically, with this pipeline in place now, we can simulate extremely high resolutions of smoke flow on a single computer. So this particular simulation has 135 million voxels and an effective finest resolution of 1K by 2K by 1K. So here the adaptivity pattern is as follows. We have more resolution near the source and the sphere to capture the nice vertical details, and then we coarsen as we move away from the source and the sphere. So this is another example to show what's the benefit of enforcing incompressibility. So basically, um, we constructed this example to show that if you don't enforce incompressibility, then the flow can be sluggish and slow. So on the right, we show incomplete Cholesky, which is actually failing to converge, and so the flow is less energetic, and you can see that it's actually also losing mass. Now, we constructed another example just to show that it's possible to dynamically change the resolution in different parts of the domain. So inside this box is 4 times higher resolution than everywhere else in the domain. And so you can see that nice vertical details emerge inside the box, but as soon as they leave the box, then they dissipate. Um, due to averaging. So um, initially, I had developed this pipeline for simulating single phase fluids, so smoke flows. But subsequently, I just wanted to highlight that I have also generalized this pipeline to also simulate liquids. And in particular, we can simulate extremely thin sheets that arise due to dynamic interaction. And the nice feature that we are enforcing here is that the liquid surface can freely cross different levels of resolution. So why is this a nice feature to enforce is because then we don't have to adapt the resolution of the adaptive grid every time the liquid surface is going to move. So that way we have more freedom in terms of adapting the grid topology, basically in terms of dynamic objects. So why is this a challenge? Let's just consider a very simple example to understand the problem. So suppose our adaptive pattern looks as shown here, and the liquid surface exactly passes through the center of the core cell. So if we look at the exact solution for the pressure, then it should be zero at the core cell and at the final top cell. And for the bottom right cell, it should be rho g h over 2. Now, this is what the exact solution for pressure should be. It is not an approximation that is given by an approximate numerical solver. So you can see that there is a pressure gradient between the bottom right cell and the core cell. And on this grid topology, it will give rise to a velocity value at the bottom face. And this is a problem here because we just want the fluid surface to remain stationary and we'll get these non-physical velocity currents. So an easy way to solve this problem is to slightly tilt this face, and if we are careful about how much we twist this face, then basically the pressure gradient will exactly match the gravity force and it will end up canceling each other, and so we'll get back the hydrostatic solution. So this is a field test of this idea on a 2D simulation where you can see that ultimately we get back the hydrostatic solution. So um, the idea here is to basically locally change the geometry of a voxel decided by its local neighborhood and convert it to that of a power diagram, which is basically a weighted Wagner diagram. And the weights here are proportional to the circumcircles of each element. And what you can show in 2D is that if you choose weights according to this strategy, then the topological connectivity of the power diagram is exactly the same as that of the quad tree. Now things become a little complicated in 3D because voxels that previously only shared an edge can also share faces now. But we prove in the paper that there are no new faces other than these that can arise. And so the complexity of the power diagram is contained to edge faces. Now, if we assume a grading restriction that no two voxels that share either an edge or a face differ by more than one level of resolution, then we can come up with a compact encoding scheme to combinatorially enumerate all possible neighborhoods. And the advantage here is that we can pre-compute all possible power diagrams that will arise and avoid the cost of Warner diagram computation at runtime. So this can allow speed up at runtime. So basically, here's a comparison showing that compared to the previous smoke simulation pipeline, which is shown in the second column, our pipeline for constructing sparse systems using power diagrams is competitive, which is shown in the third column. And in contrast, if we were not going to use our Go cell based mechanism, then you can see at in the fourth column that the pipeline is extremely slow. So another change that we did was to uh, basically use SP grid to track the dynamically evolving liquid surface at high resolution. Simply because we had this sparse data structure to give us the ability to track the liquid surface at very high levels of resolution. So we decided to see how far we could go with it. So it turns out that in comparison to existing state-of-the-art methods for interface tracking, such as particle level set, our new method can track fine details extremely well and gives much smoother solutions as you see here. And actually, we can keep on repeating this test for much longer times than what previous works have shown. And you can see that we can still capture very high amount of detail. Now, similar techniques are also used in 3D, and we can see that the result is similar. So, compared to particle level set on the right, which is actually dissipating uh, when the fluid surface becomes thin, we can give completely smooth solutions. So, there are some technicalities that I'm going to gloss over, such as substepping advection or how we basically enforce the fast marching solution on the adaptive grid. But suffice it to say that our compact encoding scheme facilitates doing these operations efficiently. So basically, we can adapt the tree topology dynamically at runtime and compute solutions that are indistinguishable as the liquid surface crosses different levels of resolution. So apart from simple examples, we wanted to push the limits of this pipeline and conduct large-scale simulations, such as water flow in this river canyon that has highly irregular geometry. And as you can see, this new pipeline can capture very nice details as water from multiple sources is merging together. So here we are using the following adaptivity pattern where we have high resolution near the canyon and we coarsen as we move outwards. So, so far I have shown you that this pipeline for SP grid can be used for efficient smoke simulation and efficient water simulation. And I just wanted to briefly mention that we have also extended this pipeline to actually simulate viscous liquids, such as what you see here. And the advantage here is that we can speed up the solution of the viscosity much faster than a uniform grid solution and still achieve qualitatively similar results. Now, the difference between incompressibility and viscosity is that the degrees of freedom now live at faces rather than cell centers. And so we are actually dealing with denser systems compared to the pressure projection. And here I've just enumerated the different variables that each degree of freedom will encounter. So it turns out that you have to be a bit careful when you compute the solution because if we are not careful and the accuracy of the operator is only till first order, then it can actually lead to stiffer solutions as we keep coarsening the resolution. So as you can see, the green solution that has three levels of refinement produces a beam that is much stiffer compared to the pink solution, which is the uniform grid solution. So you have to basically be careful to lift the accuracy of the operator to second order, which is what we ended up doing. And with that in place, we can get solutions with multiple different resolutions that reflect the accuracy of the uniform grid solution. So I'm skipping details here just because it's not really relevant for where I want to move in this talk. But I just wanted to conclude that what I have shown you so far is the use of SPGrid for designing efficient pipelines for smoke simulation, water simulation, and viscous liquids. Now, as you can see in my talk, I have told you that every different kind of simulation has its own associated challenges. And so this requires um, uh, problem specific solutions for each of these specific problems. And so if we wanted to simulate any other phenomena, the question naturally arises, is there any other challenge that is specific to that particular problem? And so will we have to come up with new solutions there also? So this naturally leads to this idea of unified computational models, um, where we want to have a single model that can allow the simulation of many different kinds of phenomena. And this is a very hard problem in physics simulation. And I'm not saying that we have solved this problem, but we have made some progress, which is what I wanted to share. So I'll basically start motivating the idea of unified computational models using the example of bubble simulation. Now, um, if you don't see the connection immediately, then please bear with me because I'll bring out what's the connection between unified computational models and bubbles as we go through the next few slides. So, bubble simulation is a topic which I had worked on during my PhD days, and Um, as you can see on the slide, bubbles exhibit very different scales of phenomena, from large bubbles that exhibit complex topological shapes to small bubbles that are more specific in their shape, and they ultimately turn into tiny spheres due to strong surface tension forces. So apart from the aesthetic appeal of simulating bubbles, these are also important for medical applications, such as what you see here. So the idea here is to subject a bubble to an ultrasonic wave of some adequate frequency, and this frequency allows this bubble to collapse into daughter bubbles and release secondary shock waves in the process. And the key concept is that if the initial ultrasonic wave is targeted carefully, then the secondary shock waves can be used for kidney stone destruction, prostate tumor ablation, targeted drug delivery, and similar medical applications. So it's extremely useful in practice. But the key thing to note is that this technology is only facilitated by the compressibility of air. Now, we also see the compressibility of air in common physical phenomena that we may not take note of. So, for comparison, there is a water dispenser, and the left one is actually taken from the pantry in Gates Computer Science at Stanford, um, whereas the right is a simulated example through the method that I'm going to describe. So, the important thing that I wanted to point out here was that conventional two-phase flow simulators will not be able to simulate this example because they do not enforce the compressibility of air. They assume air is incompressible. And so I had to change the design principles and enforce conservation of the bubble mass instead of the bubble volume. So basically, to solve this problem, I first moved to enforcing more general principles such as the conservation of mass, momentum, and energy in fluid simulation, and then subsequently considered how we can couple incompressible flow to fully nonlinear compressible flow that includes the effects of shocks and the refractions. So just to give you an example, on the left, we have a 2D example where there's a water droplet that is moving in a compressible fluid, and we are visualizing the pressure contours. So as this droplet moves to the right, it creates a shock wave in front of it and the refraction wave behind it. And on the right, there's a 3D simulation of an explosion and we have tried to visualize the shock waves that emerge that fractures all these windows. So once I had solved this problem, I made some simplifications inside the bubble, basically because we do not really care about the shocks and the diffraction waves. So I assumed that both the density and the pressure inside each bubble is spatially constant. And what this does is that in the sparse linear system, it gives rise to a single dense row and a single dense column per bubble, but otherwise preserves the structure of the sparse matrix. So the resulting solver is actually quite robust and nicely captures bubble details. Now you can see that there are not a ton of bubbles in the simulation because at this point in time, the simulation is 10 years old. So technology has continued to evolve, hardware has continued to evolve. So today we can do much better. But I just wanted to highlight that rather than just get visually nice looking examples, I had also tried to quantitatively and experimentally try to evaluate the accuracy of this solver. And basically, we had found that compared to real experiments, we can uh, quantitatively match some features, such as the steady state rise speed, which we can get very, very closely. Um, but basically, the velocity streamlines are different compared to real experiments because of a highly simplified single pressure degree of freedom model for the bubble. Now, in terms of performance, this new solver is roughly 6 times faster than two-phase incompressible flow. So um, basically, just in the last couple of years, we were re-exploring this solver and trying to generalize it to enforce certain other physical effects. So I basically generalized this formulation into a constraint-based formulation that not only supported bubbles but also supported objects acting at liquids from a distance. So the piston that you see here, it's actually moving the liquid surface, but it never actually touches the liquid surface. And this is possible through this constraint method. And compared to two-phase flow, this constraint method is also able to get qualitatively similar results for low density bubbles. Now, here is the problem that arises. So basically, for low density bubbles, um, if we change the density of the bubble so that it matches the surrounding liquid, then we see that the constraint bubble always rises. And even if we change the density of the bubble to be higher than that of the surrounding liquid so that the bubble should sink, we see that the constraint bubble always rises. And that is the big problem with this method that enforces a spatially constant pressure field. So we ended up changing the formulation here, and instead of a spatially constant pressure field, we instead looked at the velocity field and we tried to enforce some properties on the velocity rather than the pressure. So we assume that the velocity is locally affine. So u is a constant velocity value here, and g is an affine matrix. And if we do that, then we can see that we can get qualitatively similar results now, both for matching density bubbles as well as for high density bubbles. And interestingly, we can take this idea a bit further, and rather than having a single affine region, um, we can have multiple affine regions and basically get a nice method for adaptive liquid simulation. So this is where I wanted to tie up things of why I ended up talking about bubble simulations, because the principles that we learn from bubble simulation can actually be used to design a fast liquid solver. And Now the liquid solver is the adaptivity pattern inside the liquid solver is much more flexible because two neighboring adaptive regions can have arbitrary shapes as opposed to octrees where we have limitations on how much they can differ. Now in 3D also we can see that we can get qualitatively similar results at faster compute times. Um, the catch is that you have to control certain parameters carefully, otherwise you may not get the exact behavior as the uniform grid simulated. But you can refer to our paper for such details. And similarly, for dense bubbles, we can also get qualitatively similar results. And in fact, this coarsening mechanism allows you to coarsen both the region inside the bubble as well as the surrounding liquid, but at the cost of some topological features that are lost. So, what did we learn from this expression? We found that by changing the design choice from a constant pressure field to an affine velocity field, we can actually simulate much richer physical phenomena. And so the natural question is that are there some more deeper principles under the hood that allow us to um, simulate even more rich physics? Um, and this model is just an approximation of that deeper physical principle. So it turns out that that is actually the case, and this can be described through the general umbrella of non-local modeling. So basically, uh, if we just look at the function value itself, then that's zeroth order non-locality, and you can think of this as the constant pressure value that we looked at just a while ago. And if we look at the first order derivatives also, then that corresponds to first order non-locality, and this is like the affine velocity field that I just showed you. And so you can take higher order derivatives and you can get more general models. So what does this buy you? Let's just look at a very concrete example through the example of diffusion modeling. So here I've written the diffusion of temperature in general terms. And basically, if you choose these parameters tau q and tau t to be zero, then we recover the Fourier's law, which is the predominant method to simulate diffusion. But if we choose non-zero values for these parameters tau q and tau t, then we get this other model of diffusion, which is called CF diffusion, that was first explored by Anderson and Tama in 2006. So, what's the advantage of CF diffusion? Well, let's see an example here where there's an elastic hydrogel that is expanding in water. And so what we basically see is that compared to Fourier-based diffusion, the non-Fourier or CF diffusion-based hydrogel exhibits more dynamic motion. And this is not just of visual importance because actually if you look at real-world imagery for how a hydrogel expands, then you can see that it exhibits these folding patterns. And what we observed was that with CF diffusion, or more generally non-Fourier diffusion, we can qualitatively get some folding behavior for this hydrogel, whereas the Fourier-based hydrogel exhibits completely isotropic expansion and contraction. So our results are only qualitatively similar, and more research is required to see if CF diffusion is sufficient for matching to real world footage. So we did not explore that in this work, but that's an interesting problem for future research. Here are some other examples which provide non-intuitive behavior. So we are simulating ink diffusion in a fluid, and on the top left is Fourier-based diffusion, where we see a lot of dissipation due to an additional diffusion step. And on the top right is no diffusion, so just plain incompressible flow. And on the bottom, we see the effect of non-Fourier diffusion. So rather than dissipating visual details, it actually heightens them, which is very non-intuitive to how that will happen if you're adding an additional diffusion step. Now, this is one example which I'm not going to cover in too much detail, uh, but just a brief walkthrough that compared to a constant velocity in the background, Fourier diffusion dissipates everywhere, whereas non-Fourier diffusion can give you a conical spray-like pattern. That's more intuitive to what we expect to see. The example that really fascinates me is snowflake growth that we explored with this model. So I should mention here that CF diffusion is a general model of diffusion. So it can simulate both Fourier diffusion as well as non-Fourier diffusion. So with CF diffusion, we can get these top patterns which are symmetrical, and these are common patterns that we see through Fourier-based models. But we can also get asymmetrical patterns such as those shown at the bottom through non-Fourier models. And again, these are not just of visual value because there are certain non-symmetrical patterns, or I shouldn't say non-symmetrical, but rather certain patterns that cannot be described by Fourier-based diffusion, but they actually can be described through non-Fourier diffusion. So this cross pattern that you see on the left, or this hexagonal pattern that you see on the right, are both only described by non-Fourier diffusion, as we show here. And here is a quantitative comparison. So for this cross pattern, Fourier-based diffusion incorrectly predicts 6 branches, as shown on the right, whereas non-Fourier diffusion correctly predicts 4 branches. So we actually showed that non-Fourier diffusion has value for experimental description of certain observed phenomena. And an interesting thing to see would be if CF diffusion is sufficient for describing all snowflake patterns, or are there patterns that are outside the realm of CF diffusion also? Now, just for fun, we also simulated a coral reef, um, but this is not something new here because this same pattern can also be simulated with Fourier-based diffusion. And more recently, we have actually gone further and use non-local models to simulate different kinds of viscous liquid behavior, all using the same code just by changing parameter values. So the nice thing that we showed here was that the same code can define both Newtonian viscous liquids that yield symmetrical patterns, such as this classic liquid rope coiling on the top left, and it can also give asymmetrical patterns for non-Newtonian liquids, such as this shaving cream on the top right and also on the bottom, through two different viscosity models. And uh, I should just mention that these two viscosity models are accepted in the engineering community. And what we show is that we can recover these models using our general umbrella of non-local modeling. So here are some other examples showing symmetric buckling of Newtonian chocolate on the top left and asymmetric buckling of non-Newtonian cream on the bottom right. And again, these are through the same code just by changing parameter values. Similarly, we can simulate Newtonian syrup that again exhibits symmetrical rope coiling, and non-Newtonian ketchup that drops at a very irregular rate. And now that we have this model for simulating uh, viscous liquids that are both Newtonian and non-Newtonian, we can actually combine it with diffusion to model phase change. And so we simulated a chocolate bunny, as is customary of any graphosaur. So we show that basically if the bunny is viscous, then its shape is preserved for much longer as it melts on this heated pan. So this was done more for visual niceties, but the example that I was really excited about was was to simulate 3D printing through this method. And what we show is that by changing the way materials are 3D printed, we can change the elastic properties of the shapes. So um, exploring further for some quantitative validation would be a great area of research with this model. So just to conclude, I realized that writing this kind of physics software is very time consuming and expensive. So my group actually actively develops an open source library where we release our code for different projects from time to time. So please feel free to check it out. And I'd just like to acknowledge the following collaborators and funding sources that made this work possible. And with that, I thank you for your time and I'm happy to take any questions. Thank you.